Great. Hello and welcome everyone. Today we are having our first panel discussion as part of the Magnetosphere online seminar series. It's a discussion spanning GEM, Shine, and CDAR. And we have a number of people who will be talking today, and then we'll also move into a breakout and discussion session towards the end. So with that, I'll hand it off to Matthew Argyle, who will be doing a little bit more of an introduction and introducing our next few speakers.
Yeah, hi everyone. My name is Matthew Argyle, and we're putting together a set of flash talks followed by a community discussion for ethics and interpretability of AI. And this talk is sponsored by the Shine, GEM, CDAR Machine Learning Committee. We're hoping to gather resources and help people out getting into machine learning incorporating into their research and learning more about it and helping share the tools across the community. So today our flash talks are led by Aris Nerok, Abby Azari, Jacob Bortnick, Gary Duran, Doran, and Barbara Thompson. And so Aris, if you're ready.
Sure, yes. Hello, my name is Aris Narok. I work out of NASA Goddard. I am a data scientist, and my capacity here is representing the Center for Helioanalytics. I'm heading up the responsible AI portion of this group. So I want to talk a little bit about ethical AI and kind of motivate what we're doing here today. Next slide, please. So first, some definitions. What is ethical AI? And I also call it responsible AI. Some of us prefer this term because often when we start talking about ethical AI, people immediately hone in on the ideas of autonomous vehicles or autonomous robots and their actions. But ethical AI encompasses much more than that. So in this definition, ethical AI is artificial intelligence that adheres to well-defined ethical guidelines regarding fundamental values. So these are the important aspects here. Ethical guidelines that are defined and they're representing fundamental values. So an organization that applies ethical AI has clearly stated policies and well-defined review processes for adhering to these policies. Next slide, please. So basically, I'm here to say, what does this have to do with you? I'm not creating a robot. Next slide. The bottom line is many of our funding agencies are starting to move towards codifying their thoughts and limitations regarding ethical AI and guidelines for trustworthy AI. Specifically, I'm going to talk with reference to the NASA framework for ethical use of artificial intelligence. It just came out this April. This is where I work, and so that's I'm most familiar with this. But most of these documents are touching on very similar values and high-level concepts. So it's we're seeing everything from the EU all the way down to NSF and DoD across the globe. These things are coming out. Next slide, please. So the NASA framework highlights six ethical principles: to be fair, to be explainable and transparent, to be accountable, to be secure and safe, human-centric and societally beneficial, and also scientifically and technically robust. And if we think back to the original definition here, these are what NASA is calling their fundamental values. Now, at this point in time, these are this is a very high-level recommendation with no actionable items defined yet. Those sorts of documents are in process. And at the moment, a lot of the focus is around higher level software involving autonomous vehicles or, flight operations, but all the discussions they're having and even these fundamental principles that they have outlined in their framework document are expected to apply all the way down through scientific research, post-mission data, that sort of thing. And so we need to start looking now so we're prepared to adhere to these new requirements as they start coming out in the next few years. Next slide, please. And when I look at the 6 principles and I think about much of the work that at least I see being done within the Center for Helioanalytics, and I think in this community in general, 2 jump out at me as being especially applicable. And that is the one, this blanket requirement that AI code is explainable and transparent. And on the right-hand side here, you see the actual text in this framework document. And they highlight that AI logic and decisions must be explainable. What that is not yet well defined, although as you'll see in some of the talks today, there's a lot of work in the community towards moving in this direction. And then also any work with ML and AI should be scientifically and technically robust, adhering to the scientific method, well tested, well documented, peer reviewed. And what we need to consider as we move forward is how, as a community, do we define well documented, well reviewed with these new emerging analytic technologies. So that's really what I want to say today. You can go to the next slide, and you'll see these when we hand these slides out. Just some of the references of the documents that we talked about. But we as a community need to move towards more explainability, more interpretability as we start to use these machine learning and artificial intelligence models, because the requirements for this are going to be coming from the outside soon. Thank you.
All right, thank you, Eris. Next up, we have Abby.
Great. Hi, everyone. I'm Abby Azari, and my apologies for keeping my video off. My internet has been a little in and out. So just to start off, I'm mostly working in a field of planetary space physics, and I wanted to talk to you today about where heliophysics and planetary science are with machine learning, and then go into a brief introduction of what has been started to be called interpretable methods. So Matt, if you could go to the next slide, please. Great. So what is machine learning used for today? These are mostly examples from planetary science and heliophysics. And really throughout the mission life cycle, you can see different aspects of machine learning. So we have pre-mission planning, where machine learning is often used to start to plan out trajectories. There's mission operations, which gets a fair amount of attention in regards to automation as well as prioritization of observations. And some of these systems are being deployed actively already. And then finally, I would say what's of most interest to this community is post-mission analyses. So you already have the data, or you're getting data at the moment, and you're trying to understand what this data is telling you. And this is a pretty rich environment in general. So next slide, Matt. And given that machine learning is quite active, I think it's good to start to understand what is machine learning. So at its most basic, machine learning are computer algorithms that improve or learn through the inclusion of data. And this is a very broad definition that I think it's useful to keep in mind. These methods are highly flexible. So they're designed to adjust their parameters to a structure of data they have access to, and are mostly used to produce models that make predictions. So keep going. These range in complexity from its most simple of linear regression, as well as to neural networks, which are quite popular right now. And applications really range across the board. And this is where it comes in for this discussion, which is how these methods are suitable for us in the scientific community is an area that we're still exploring. And we're still discovering novel ways in which we can use these as they become part of our toolbox. So given this, I want to move towards, who's publishing and what are they publishing in regards to machine learning. Next slide. So what this figure is showing you is the percent of published works within each field. So planetary science, earth science, heliophysics, and astrophysics. How much of that field is publishing about machine learning? Okay, so these are all normalized to each field, so we don't have to worry about astrophysics being a larger field, say, than heliophysics. And so what you can see is all of these fields have had an enhancement or an increase of machine learning over time. And when you start to break down what these publications are talking about, you find that the majority of machine learning literature tends to focus on neural networks and deep learning. So it ranges by field, but this represents about 40 to 60% of these applications. So next slide, Matt, thanks. And given that these methods are being actively used today and they're increasing in popularity, I think it's good to sort of take a step back and ask ourselves, how can we use these methods to answer questions like, how confident are we in the trends that we see? So this vaguely falls into uncertainty quantification. And then what do we think is the underlying causes of these findings? And this leads you to an area which is often called interpretability or interpretable models. And in essence, what interpretable models are is models that follow some fundamental underlying physical rules, constraints, or functional forms that allow for human understanding. And the question then for our field right now is, how can we design our models to handle our data sets? And our data sets are often characterized by having sparse data, which is spatially and temporally varying. We also have uncertainty. And really what we want is to have these models give us interpretable output for our questions. So next slide, Matt. Great. And so how does this sort of fit into the tradition of our field, right? And so I like to think of this as existing on a continuum, where on one side of the continuum you have methods which are model bound. And model bound methods, you can think of them as advancing, say, a physical model over space and time to understand something about a physical system, right? So on the left here, I have magnetohydrodynamics to understand plasma transport. I would consider that a very model bound method. Then on the right, you have something which is model free. And by that, I mean, you don't necessarily care what model you're using to understand the system. What you care most about is the prediction of some quantity. So in this case, you have something like deep learning for solar flare prediction, right? And this, referencing back to a previous slide, this is what counts as 40 to 60% of the field right now. They're very interested in deep learning and neural networks. And then in the middle is something which has been increasing in popularity over time, which is how can we take advantage of the data that we have available, but we also want to include our physical knowledge so that we can better understand and increase the transparency into our findings. And so this is called a lot of different things these days. This has been called model adjusted, it's been called theory guided, it's been called interpretable or physics informed. And there's a nice hyperlink here to Rudin 2021, which has a good overview of what interpretable models mean in this context. So next slide, Matt. And within this space, there's a range of current and emerging methods. Two leading ones that I wanted to spend a bit of time on. The first is something called Bayesian Methods. And depending on how you define machine learning, as well as AI, you can or cannot include Bayesian methods in those. But most often, Bayesian methods are considered to fulfill the definition of interpretable. And I'll talk about that next. Before we'll transition to Jacob to talk about physics-guided or physics interpretable machine learning. So next slide, please. So what are Bayesian methods? And before I start, I want to have a bit of a disclaimer and say, a 4-minute overview is not going to be able to cover this field that successfully. It is a rich field in and of itself. And so I encourage you to do your own research if this is of interest. But in general, Bayesian methods follow Bayes' theorem. And the difference between Bayesian methods and, say, other statistical methods is that Bayesian methods incorporate how we understand the system in order to update probabilities about the observations. And those two key points make them a good fit for the type of interpretable machine learning that I was talking about before, because they allow you to incorporate, say, your physical understanding to then generate and estimate your confidence in the observations. So next slide. And I want to just give some very brief perspectives for implementation into our domain in heliophysics. And some of the advantages are that they are inherently interpretable. So from design to implementation to assessment, when you're doing Bayesian models and Bayesian methods, you often are required to invest significant expertise into the domain that you're interested in. Next slide. And because you include your prior understanding or your prior information, this is a really natural avenue to include your physical knowledge into these models. Next slide, please, Matt. Because the posteriors or those final outcomes can be constructed at various levels of confidence, this allows you a natural avenue to include uncertainty as well as sampling concerns. Next slide. And then, of course, I wanted to have a slide about why these methods aren't as widely used as, say, neural networks in our field right now. And there is some inherent structural choices that you have to make when you're applying these that create barriers to their implementation. So oftentimes we're not educated in these methods. And so when you start off, these are much harder to use, sort of out of the box, than several other methods. And so what I'm going to say is these methods provide a good way to include your physical knowledge. They do take a little longer to implement and understand. But in general, I find that they are a good way to start to address this discussion about machine learning, interpretability, ethical AI, etc. So now I'll transition to Jacob.
Okay, hi, good morning, everyone. I'm gonna pick up the baton where Abby has left it off. And specifically, I'll be talking about basically what Abby mentioned about this idea of interpretability. And in one of her points, she made the point about mixing together physical laws and constraints into our machine learning model in kind of a number of different ways. And so what I'm gonna do in my brief 4 allocated minutes is I'll talk about 3 basic ideas in the community right now. And there are more, of course, but these are just kind of 3 very interesting and promising ideas of mixing together physical insights into machine learning models that are inherently kind of black box. And we're trying to inform them or get things out of them that are interpretable and more understandable to us. I think I know most people on the line, but for those who don't, I'm Jacob Bordnick. I'm a professor at UCLA. My interest is in magnetospheric physics, specifically inner magnetosphere, high energy particles, and machine learning methods, and just figuring out how we use this really powerful and interesting technology to help us do our science, in the presence of very large amounts of data coming down these days. Okay, so with the intros done, let me talk about my first topic here, and it's highlighted in yellow. It's called PDE discovery. We know that most systems in nature can be described by a set of partial differential equations. In other words, relating spatial derivatives to temporal derivatives of some quantity to tell you how that system varies over time. Now, what can machine learning do for us in this area? Well, one very interesting area of machine learning is to basically discover automatically partial differential equations that best describe some kind of an evolving spatiotemporal system. And so if you think about it in space science, this is all we deal with, right? We deal with spatiotemporal systems, things that vary in space and in time. And what we would ideally like to do is we would ideally like to have some kind of a computer algorithm go out, harvest a whole bunch of data over a large amount of time, and just be able to describe it for you in a partial differential set of equations. A lot of times we have an idea of what these should be. Sometimes we actually don't. I mean, you can go to distant planetary bodies, and instead of collecting terabytes of data that you have to transmit over a tiny little pipe, you can instead transmit some equations, right? That's really what we're after as scientists. Okay, so how do we do this? Here's an example from Rudy et al., one of my favorite papers on this topic in 2017 in Science Advances, called Data-Driven Discovery of Partial Differential Equations. And they illustrate the methodology right here on this Navier-Stokes simulation. So if you look at panel 1A below, what you see there is kind of a Navier-Stokes flow field around a cylinder. It's a little hard to see, but it's a little cylinder on the very left. You have a flow field, which has pressure, velocity, and vorticity that they deal with here. It's a data sample at a bunch of spatial points and a bunch of times. And the basic idea is you pick a point and you look at your quantity, let's call it velocity, and you see how it varies at that point as a function of time, df by dt, right? And then you take spatial derivatives around it. And you build up a library of the other various physical quantities, the derivatives in x, y, and z of that quantity, the second derivatives, third derivatives, mixed derivatives with other quantities. You create a library of terms. And the magic is that you use linear regression, but in a way that enforces sparsity, picks out only a few dominant terms. And lo and behold, in figure 1c, you solve the sparse regression problem. And in panel D, as you can see, what we've done is just from the data alone, the algorithm has been able to pick out very reliably the Navier-Stokes equation. You can do this in a regular grid. The kind of set of panels below, 2A, 2B, 2C, does this with kind of sparsely sampled irregular points, more of what you would expect to see in a satellite measurement or some kind of a physical measurement system. So that's part one, PDE discovery. Let's go to the next slide, please. Part two is physics-informed neural nets. And it doesn't necessarily have to be neural nets, but that's usually what it's implemented in. And so what's the basic idea there? Well, let's say you have measured a bunch of points in your system, for example, in a satellite over some period of time, and you want to create a neural network that will reconstruct that system for you. Let's say the quantity you measured is magnetic field data, Bx, By, Bz, in a system over some period of time. And that's what I'm showing in the panels at the bottom here. And so have a look at the top left, the original data. These are just two dipoles, kind of like an Earth's dipole, which is little and on the right-hand side, and a very large distant dipole representing perhaps the solar wind or flux rope or something. And so you have these two dipoles, you sample the data sparsely, and you can create a neural network model to reconstruct that, which is what you see in the next panel, alpha equals 0. This works very well, but if you cast your eyes down one panel below it, what you'll see is this is just the same data, but it's evolving as a function of time. You'll see a couple of kinks and wiggles that don't look right. In fact, what is happening is the machine learning is using its sparse data to reconstruct the data as best as it can, and that's what it comes up with. But it doesn't know that there are some physical constraints on this. So going back to Abby's point, we want to bake in some physical constraints. It turns out that in a neural net, you have a cost function at the very back of the model that is trying to be minimized. You're usually trying to minimize the mean squared error between your model predictions and your data at the points where you have data. But it turns out that you can actually jimmy this little cost function a little bit, and you can introduce another piece. And this piece, you can make the model enforce some kind of a physical law, a constraint, a conservation law, anything. So right here, what I've done is I've introduced an extra piece. If you look, loss is equal to MSE, which is mean squared error between model and data, plus alpha, which is kind of a weighting parameter. del dot B, divergence of B. I'm telling my model, don't only focus on the mean squared error, also make sure that you are respecting divergence of B. Try and make that as small as possible. And you'll see the panel, the 3 panels on the right, alpha equals 0, 1,000, 5,000, is different weightings on the physics informed part. The physical constraint tells you how strongly you want that physical constraint to be respected. And as you can see in the bottom panel on the right-hand side, those kinks and wiggles have gone away. Now we have a just about divergence-free magnetic field model. So you can use fewer points and you can have a much more physically realistic model, and it's interpretable, right? You can now interpret this model better. So let's go to the last part. I feel like I'm running a little short on time. In recent years, and by recent I mean last year, almost to the day, October 30th, we had this really interesting breakthrough paper. It made a whole bunch of news. I believe MC Hammer even tweeted about this. You can't touch this, apparently. And so the idea there is if you have a bunch of PDEs that accurately describe a system, you can use an AI-based methodology to solve these PDEs. And this can go thousands of times faster than current, time domain-based PDE solvers. It's accurate. It can do families of PDEs. It's very exciting because, things that are done in supercomputers now should, in principle, be able to be done in the near future on your laptop at 1,000 times lower cost computationally. So this has caused quite a stir. It's a topic that I admittedly do not know a whole lot about, but it's something I thought I'd bring up as part of this presentation to make the community aware of it. So those are my 3 points, and I think I will hand it off right there.
Okay, thanks, Jacob. Next up, we have Gary Doran. Yeah. Gary, are you there?
Yeah. Hi, thanks everyone. My name is Gary Doran. I'm from the Machine Learning and Instrument Autonomy group at the Jet Propulsion Lab. And switching gears a little bit, I'm going to be talking about some insights from a recent collaboration between JPL and the Aerospace Corporation. And this is about applying this trustable AI or machine learning framework specifically for technologies that are to be infused on board spacecraft to help them operate more autonomously. Next slide, please. Yeah, thanks. So the key objective here was to take this existing framework that the Aerospace Corporation had developed for building trustable AI and apply it to 2 use cases that we had at JPL. And generally speaking, these use cases, as I mentioned, they're for use on board a spacecraft. In one case, it's summarizing large quantities of data that's on board to extract the most scientifically relevant information and send that back to Earth. And that's for cases where you're operating, say, in the outer solar system, where there's very limited downlink bandwidth and you can't downlink all of the raw data. And the second use case is a case where you want to be able to use data on board to make decisions for things like autonomous navigation. And historically, building trust in these technologies with various stakeholders on the mission has been a barrier to getting them infused. So we were interested in using this framework to help build and establish trust in these technologies. And then the Aerospace Corporation was interested in getting feedback about how well their framework applied to these particular use cases. Next slide, please. Yeah, so this is an overview of generally what's included within this framework. So there are 3 key principles that are meant to roughly mirror the development or mission lifecycle. So the first principle here is the objective and data specification. So this is making sure that you've clearly specified your goal and you have some objective or quantitative way of measuring whether you're achieving that goal or not. And then that you've clearly specified the data sets that you want to use in order to measure that objective and quantify it. The second attribute here is the focusing on these attributes or metrics of trustability. And so those are specifically reproducibility of results, confidence and uncertainty estimation, adversarial robustness, interpretability, familiarity, and fairness. And here I wanted to stress that within this larger context, we saw interpretability as one necessary but potentially not sufficient attribute to focus on for making sure that the folks have trust within in the system that you're developing. And finally, then there's this monitoring and control phase. So particularly for these types of applications that are deployed and operating continuously, you want to make sure that that you're monitoring their performance, specifically monitoring the objective that you specified earlier. And in terms of control, making sure that there are essentially guardrails in place so that if, say, the environment you've deployed the system to isn't exactly analogous to the data that you use to train the system or to evaluate it during development, that there are ways that you make sure to safeguard the larger flight system from anything that might go wrong with the autonomous component that you've developed. So in the interest of time, I won't go through all of the findings that we had through this collaboration, but essentially one of the key findings was making sure that you're thinking about the stakeholders, the people whose trust you're trying to gain through this process. And so for our particular use cases, that includes things like the science team, the larger science community, the funding agency like NASA, and then the flight engineers who'll be writing requirements, performing V&V, and then the operators who actually be interacting with this sort of system on a regular basis. And then on the next slide, if you're interested in more details, there are a couple of papers that we've submitted to the IEEE Aerospace Conference that talk about our experience applying this framework to these use cases, and then sort of a more generalized version of the framework that is targeted specifically to these onboard use cases. That's it, and I think then I'll hand it off to Barbara. Thanks.
All right, thanks, Gary. And we'll send out these slides afterwards if you're looking for any of these references. All right.
Yeah, so I hope you appreciate this brief overview of kind of what interpretability and explainability involves. I want to close out with some real reasons why we want to focus on this for the future. And it comes down to studies that have been done, including one at NASA, where we've looked into the reasons why incorrect results make their way into the literature. And many AI fails are traceable to sometimes poorly performing statistical models. However, a good practitioner can usually catch when a statistical model isn't performing correctly. We found that most of the times that an AI fail or an incorrect result appears in the literature has to do with the translation between the contextual or subject matter regime and the informational regime or the computational regime. Now, the goal is to take a computer and do something statistically or computationally sophisticated with it so that we can gain more knowledge. And sometimes the failure point is not just the translation to the computer, but the translation back. In other words, a statistically valid result may not necessarily be a contextually valid result. It takes this extra step, which is why explainability, interpretability carve a pathway to this. So can you go to the next page? Oh, sorry. And so what does interpretability and explainability bring to a publication? Simply put, it makes your incorrect results less likely to show up, and it can make correct results even better. When Abby was talking about how certain are results and how do we understand them, those are both very important parts of bringing your publication to the community. Paper isn't supposed to just tell you what you did, it's supposed to tell you what the significance of it is and how our understanding of the subject matter has been advanced by it. And so explainability, interpretability, which I'm using interchangeably in this case, because it both work for this case. They help the authors more likely to detect a flawed result. It helps them translate that result into the subject matter domain and ensure that there's robustness. And it also helps reviewers understand and validate these results and even reproduce them. So I will close out. I had a whole bunch of questions. Thanks to the editors who helped me assemble these questions. The next slide, please. Many factors involved whenever it comes to this, because it's very difficult to do a prescriptive approach, but a descriptive approach as into what is an acceptable level of interpretability in order to make it a scientific publication and not just a technical report is addressed in these, is covered in some of these questions. So I'll leave it to you guys. We'll share the slides later because I think we want to move on to the discussion, right?
Yeah, that's right. And so the plan for the next 22 minutes is to the plan for the next 22 minutes is to take 11 minutes and break everyone out into a breakout group of about 4 to 5 people, where I'll post this, these 2 questions here. What do you need to see for a model to be interpretable? And what is the role of explainability and interpretability in scientific publishing? And to answer those or any of the other questions that are on Barbara's slide. And so I'll shuffle people around a little bit just so that all of us organizers are in separate rooms. But the goal is to introduce each other to one and then break out. Oh, yes. Okay. So the link is in the chat.
All right, great.
Yep.
Thanks for the link. One quick question. I think for our YouTube viewers, what we'll do is just keep this main session open as like an effective breakout room, and then you can put some of the other people into those other breakout rooms if you'd like to do it that way.
Okay. So I'll break everyone out into, there's 30 people, 6 rooms, and then discuss. So we'll see you back in about 10 minutes. Okay, are people in this waiting room here?
Or in the main session? Yeah, I think that works. Session. We could have sort of a little discussion here as if it's a breakout room. And that way YouTube can at least hear, even if they can't participate audibly. But.
Yeah. Can I, let's get this guy some.
Hey guys, what's up? Jay.
Hi y'all.
Hey Jay, what's going on?
Okay,
just trying to learn a little about, machine learning. So I have a serious question, minor question. There was some work on nonlinear dynamics, I don't know, 10, 20 years ago, before ML became, a buzzword, but on discovery of underlying equations of motion, given kind of time series, anything about that at the time. People would, maybe take a simple iterated mapping or whatever, generate a bunch of points, and then try to infer backward what the underlying, shape of the attracting surface, or maybe even the, equations of motion that generated them were. Is there any connection between that and your discovery of the PDE's business?
I think in
Sounds a little similar to me. And in both cases, it's, they're not necessarily trying to uncover the quote unquote true equations of motion, just ones that reproduce the data.
Yeah, that's a really good question. I mean, hello, Jay, did you disappear?
Yeah, I think just turning the
No,
video.
I'm here. I'm here.
All right, okay. Yeah, I mean, the folks that do this kind, I mean, so Rudy comes from the University of Washington, works with Nathan Coots. And so Nathan Coots is a big kind of dynamical systems guy. So he does exactly what you just described, right? Take a time series, find all sorts of clever ways to kind of model that system as a time series and come up with some description of it. And so he kind of comes from that background. The current method, though, is quite different. The current method is very much more machine learning-y in that you're trying to fit some terms to other terms as opposed to a kind of a dynamical system discovery. So I think at least superficially, I would say they're kind of different. They're different in flavor, but it's the same folks that do both approaches. So maybe not surprisingly.
So is it not just that you're fitting kind of the points, X, Y, Z is a function of time, but also their derivatives, basically. You've got a bigger set of basis functions when you're doing the fitting, essentially.
Yeah. So there are, a couple of things I glossed over pretty quickly. So you're basically fitting a time derivative, df/dt, at some point to a bunch of quantities and derivatives of those quantities on the right-hand side. So the question is to create, or what do they call it, an overfull library, right? A library of candidate terms, and then have the sparse regression pick out what the right spatial derivatives are. So, okay, what if you don't get the right terms into there? So that's a problem, right? You have to kind of guess everything possible and hope that the right solutions are part of your library so that the sparse regression can pick them up. That's one.
You also have to estimate, continuous derivatives from sparse discrete data, right?
Yeah, so that's another thing, noise, right? So noise, which...
all right, noise, I think that's separate from discretization. Noise means the measured values aren't quite right, but even if they are, it's hard to get a derivative from discrete samples.
Yeah, okay, so I'm including discrete and sparse sampling under the big heading of noise. In other words, you're now interpolating back from your points to some smooth functions, right? And so you're introducing error in that way. The point that I'm making is when you take derivatives of noise, you kind of amplify the noise, especially at the high frequencies, right? It's like cosine of omega t, take its derivative, you get the omega term out front. And so you're amplifying the high frequencies. And so that can become a problem. So sparse sampling, noise in the system, any kind of noise or error can definitely throw off this method. But people are working on ways to kind of try and beat down that noise and beat down the sparse sampling, which is a problem pretty much in every context that you apply this PDE discovery method, right? You're never going to have perfect sampling.
I can also imagine you're kind of discovering one by one all the terms of the Taylor expansion of the real solution, but you may not recognize what it's the Taylor expansion of.
Yeah, and in fact, one of our new hires at UCLA, Paula Alves, has that's basically his main topic is reduced order models of systems. And so start off with a pick equation and do your machine learning PDE discovery on it. And you can basically pick out different approximations of MHD in principle and in practice. I mean, he's shown that you can do this. And so that's exactly it, right? It's like a Taylor expansion. It's like moments of the loss of equation.
But again, it would rather, at some point be able to have the insight that, these these terms are the expansion of, some closed form solution you already know, rather than just an approximate, a serious expansion of it.
Okay, so sorry to interrupt, but that it usually gives, if I close all the breakout rooms, it usually gives like 1 or 2 minutes warning, right?
It's 1 minute.
I think so,
Okay.
yeah.
All right, so I'll call everyone back in about 30 seconds.
Okay. And actually, just to add to that discussion there with Jacob and Jay, I mean, I guess one interesting assumption is that even though it's certainly analytically preferable to have, say, a closed form or say a equilibrium solution of the Vlasov equation, you just plug it in and can compute things without having to, do any statistical estimations. But on the other hand, I guess if there are systems, let's say, for instance, if the plasma isn't truly a Vlasov plasma, you'd have some unknown collision operator there, and who knows how that's acting in position space or velocity space for that matter. And maybe having kind of just letting the machine pick out the form. I mean, I guess what I'm saying is we could have some bias in even assuming that a plasma follows a certain closed form equation, even though some of them, of course, are trustworthy. But it's just interesting to think about, like maybe there are certain assumptions that are baked into our using of closed form equations, whereas these methods wouldn't be, wouldn't be biased in that way.
You can sit on the couch, Maxwell.
Yeah, and I think that's the point, is that if you send, autonomous probes somewhere that you cannot access and have them write down some equations for you, you may come up with terms that you didn't know about. That's the whole discovery aspect of this approach, at least in theory. You're muted, Jay.
I just don't have anything more to say.
Okay, people should be coming back in about 10 seconds.
Right, yeah.
Quick 10 minutes, I'll tell you what.
Yeah. My response to the question you put in chat, Jay, is that you need to have your AlphaCat must be finite, because div B is a constraint, but it does not uniquely determine the solution. So you have to have some of that other element to the loss function in order for it to work at all.
Yeah, to implement the approach, I understand that. I think that Jacob may have made a Freudian slip in his presentation where he said, you'd like to make the error as small as possible. And I think he meant the error in that term as small as possible. But of course, you can make it 0, but then, as you say, you're not going to be able to get anything else out of it. So, there is the inevitable trade-off in that approach between something that you ideally really perfectly want to enforce and, the thing you're trying to work with. So, 10,000 sounds like a pretty big value of alpha, but
I'm gonna interrupt here. I'm going to interrupt here and sort of get us back on the topic of interpretability and ethics in AI. We have people coming back from our breakout rooms, and I'll just call on a couple of the presenters and have them call out someone in their group for what they had enjoyed talked about or heard from during the talk. So Harris, if you want to call out someone, pick on someone from your group.
Well, I was hearing from Christine just as we kind of went back to the main group, but maybe Christine, would you like to highlight your experiences with machine learning here in the community?
I can unmute myself. So I dabbled with something a long time ago about trying to use a simple neural net routine to classify power spectra. It didn't work very well because there were too many features in the data set that looked like the thing that you're looking for, but was not that thing. And so I kind of gave up on it. But now when I go to meetings, I'm getting a lot of pressure from people to use it for things where it's not really appropriate. And people don't want to listen. And this experience is coming from the faculty member that I work with, Craig Kutzing, has been involved with a faculty member in our electrical engineering computer science department who does machine learning and is working on automated detection methods for whistler mode course elements. And even having someone who is an expert to do this and having a feature that's been documented and described, like in hundreds of papers, it's really, really difficult. And so when I go to a meeting and I present something that it's not a problem, and we have people who have never tried to use this technique before or haven't used it on this specific problem come in and say, oh, just use machine learning, when they don't understand what the data set is or how small it is. It's really frustrating. And so I think that there needs to be, instead of this blanket, like apply machine learning to everything, there needs to be more of a discussion about when is it actually appropriate, instead of just everybody must use machine learning all the time now. Anyways, that's been my experience.
Yeah, it definitely takes expertise from multiple domains to apply machine learning to a problem. And so I guess that's part of an issue with the ethics, in that you can't, if you don't really know what it's doing, then you need to be able to interpret it, I guess. And that's where the funding agencies are going, so that you can make when a machine makes a decision, it's all of the domain experts that are involved would sort of have a consensus on what it's doing.
I guess if the output of it is a fit parameter, you don't care as much about how it got it, because you have the answer and you can evaluate and test it, regardless of where it came from. Right. A lot of codes, are used by people who didn't write them and don't really know what they're doing, but they'll take the output and verify it independently, right?
Yeah. So that's a subtlety between interpretability and explainability that we didn't really get into during the talk. But one is sort of understanding it from the ground up, learning all the details that go into actually creating the model, versus just being able to take the results and sort of understand how they apply to the domain in question. Okay, so Barbara, would you want to call out anyone in your group?
Well, I think, Stephen had a very good question. If there's if there are people who are familiar with MATLAB, I couldn't really answer it because, but is there anyone there with MATLAB who understand the types of packages? So I think that's important for us to kind of close with, is if someone is interested in implementing AI, explainability, interpretability. There are some in Keras. There's Python. There's libraries that do saliency and thing. Does anybody have any advice for someone in MATLAB? What kind of interpretability and explainability tools are out there?
Yes. Firstly, hooray for MATLAB. And secondly, as a general rule, I would not advise people in our community to start rewriting AI or machine learning codes. It's like rewriting FFTs, right? Someone has done it very, very well, and it's optimized. And so I would lean on libraries, at least to first order. MATLAB has its own machine learning library. It's beautiful. There's a GUI. You can access functions directly. So I would just look into that. There's some parts in the statistics package, and I believe that machine learning is its own package now in the latest MATLAB version.
Excellent. Thank you, Jacob. We should put those in the slides at the end, just as for reference.
Yeah, Stephen, I see you have your, did you have a question or a comment?
Okay, thank you so much, Jacob and Barbara. Barbara, yes. Barbara, yes. Yes. So actually, I've used it, and you see, in physics, let's say you are doing prediction. Sorry for lecture, it's a little bit. Let's say you have something like this. Can you see it? You have from here to here. Okay, you have a data that starts from A to B. That's a data set. Let's say you have drawn, you are visualizing your data in. Okay, you have the actual data, and then you have the predicted data. So we expect the predicted data to be higher than the actual data. by some error. I think if I'm wrong, you guys are the experts. So I'm asking here, let's say now that I want to visualize this data in my plot. So which one should I take? Should I go to take because we have the target and the output, because now in that case, so I want to visualize to distinguish between the two so that someone can say, yes, this one the predicted data and this one is the target, the actual data. So in that case, how can I go so that I can, because I used the validation data, but I'm not sure if I'm correct. I use the validation data and the unvalidated data.
I see. Well, there are so I think sounds like you're dealing with a couple things. One is that you're wondering if even the model performed in a reliable way.
Yes,
you know,
yes.
kind of the two things you typically look out for: overfitting or bias. You know, whenever your model seems to perform well, but you're tricked into it by the way that you've set up your test. And there are fortunately there's some good articles that we can share on kind of that. And then when you want to dig deeper, when you're pretty sure that statistically it's working, but it actually makes sense physically, then there are different things. But I think we'll try to post some notes on that. I think Jacob had some good advice for how to do that physically, but it's a long road. You know, it's difficult to trust a computer. Because you're trying to turn it into knowledge, right? You're trying to take something that's something you understand and use a computer as a tool, as kind of an extension of your mind to do something your mind can't do easily, but you still want to bring it back in. And it's never, you know, and I think you're a good physicist in that you never fully trust it, right?
Yes. Thank you.
Okay, thank you. We're on the hour now, so I just wanted to put a plug in again for the Shine Gem CDAR Machine Learning Exploratory Committee that our presenters are a part of, including myself. And if you have questions or comments, concerns, or looking for a way to get into artificial intelligence or machine learning in your research, you can feel free to reach out with us, and we can share resources.
Excellent. Well, yeah, thank you, Matt, again, and definitely a big thanks to all the speakers who presented and the breakout discussions. It was fun to kind of mix up the routine here. And on that note, before folks leave, I do want to mention, of course, next week we'll be continuing again. We have Professor Ying Zhu who's going to be presenting on unsteady magnetopause reconnection under quasi-steady solar wind driving. So be sure to return for that, and we'll hope to see you again next week. So thanks again, Machine Learning Panel. Really appreciate your time.
Thanks for having us.
Yeah, thank you, everyone.